Okay. Well, I want to thank you all for inviting me. It's a pleasure to be at the PIRE meeting. It would be a greater pleasure to be there in person, but that obviously is not going to happen this year, so we've all had to make adjustments. The talk I'm going to give is pretty much the same one as I gave at the NSF reverse site visit, which was just about the last trip that people had going to NSF. After that, things really shut down, and in fact I gave that talk by Zoom as well, because I was beginning to worry about getting on airplanes at what was the beginning of the pandemic. So what I want to talk about really is two things: some of the work that we're doing and have been doing for a number of years and now are doing in context of the PIRE on thermodynamic structure properties of polymer-derived ceramics and related materials. Largely this is a collaboration with Darmstadt, but also to talk a little bit more generally about international collaborations that we've had, the students have been involved, and how PIRE has really helped things happen. So let's see if I can make these things go forward. Yes, excellent. So before I start the talk itself, most of you know that I moved from University of California, Davis to ASU last October to assume a professorship here, and also to help lead a new center we have, which we call the Navrotsky Eyring Center for Materials of the Universe. And for me, this is a homecoming because I started my faculty career here at ASU 50 years ago. In fact, the day that I and the dogs arrived in Tempe was within about 2 or 3 days, couldn't quite place the timing, of the day in September of 1969 that I came as an assistant professor. So it seems like life goes around in all sorts of circles, and it's been very good being here. So having said that, I want to talk a little bit about the Materials of the Universe Center. It's separate from the PIRE, of course, but what we've realized is that with the discovery, both by landers and by unmanned missions and by space missions from Earth, that the variety of planets is staggering. That even in our own solar system, the diversity of the outer planets and their moons has a lot of chemistry, a lot of things going on. They're not just dead blocks of uninteresting blocks of ice. And if one then goes and expands to the thousands of exoplanets that have been detected mostly by somewhat indirect means, and where we know something about where they are, what sun they're around, what their rotation is, what their size is, perhaps what their density is, maybe a sniff of their upper atmosphere. This presents a whole new view of thinking about materials, of thinking about cosmology, of thinking about geochemistry, and of bringing all of these things together. So the purpose of the center is really twofold. One is to use all the techniques and understanding that we've developed in physics, chemistry, material science, geology, geophysics, planetary science, astronomy, and bring these together to really a quantitative physical picture of what the universe is made of what the planets are. And in a sense that understanding planets, the solar system, and outside it is what I call the biggest inverse problem in material science. A forward problem is you have a material, you want to know its properties. An inverse problem is you have some properties and you want to know what the material having those properties might be. And that, of course, is the name of the game in thinking about planets that one cannot set foot upon. The second part of the center is that for space exploration, one needs materials. One needs materials in spacecraft, one needs sources of energy, one needs protection from radiation, not just for people, but for the equipment. So the ability to tailor materials to the extreme conditions that one will have for work in space exploration is another goal of the center. So I've come and we're starting all sorts of activities in the center. Indeed, we've hired an additional faculty member, and progress is a little bit slower than we would like because the COVID pandemic has put a lot of questions mostly into the university budget, but I'm very excited. And there are, in fact, some relations between what we're doing in the PIRE and planetary problems, and I will mention those a little bit as I go on. So I'm back at ASU. We're setting up the labs. We're continuing to do a lot of science. We're continuing to work very much with the PIRE and with people, and I will talk about that a little bit as I go on. So we had a long collaboration with Technical University of Darmstadt, Germany, Professor Ralph Riedel's group, and particularly Gabriela Mera and Emmanuel Ionesco in that institute, and we've really collaborated over 15 years, something like that, working on the properties primarily of polymer-derived ceramics. We had 7 wonderful years of an NSF, International Materials Institute program. The whole program went away, and therefore we did not have a continuum of funding in that. The PIRE has brought a number of these things back, which I'm very glad of. And also then there is a collaboration within Germany that the Darmstadt group is part of, and that indeed some of the PIRE people are participating in as well. So I laugh and call Darmstadt sometimes my home away from home, because I've spent a lot of time there. Our students have spent a lot of time there. And indeed, one of the students who just finished her master's thesis with us at Davis, Casey, spent a lot of time in Darmstadt, and we're now writing up her master's thesis for publication. So, PIRE student involvement this year, I'll focus on this year. Casey has finished her master's. In fact, now she's going back to what her first love is, which is art ceramics, ceramics in the sense of making pottery, and she has some great opportunities to continue. So, in fact, she was hoping to be part of this meeting, but she probably is not, because she also has a teaching job. So this year we were supposed to send a student to Germany, and we went through a long process of identifying a new undergraduate student. We had, in fact, a tremendous number of wonderful applicants. We thought we had everything settled, and then, of course, we all stopped traveling. So the good news about stopping traveling, if there is any news, is that we had money for a second student, since we have 2 students who are now here at ASU. Both are undergraduates in chemical engineering. Isaiah Morris, who was the original student that was going to go to Germany on the PIRE, is basically staying here this summer. Hopefully he'll go next summer. And Alex Holler, who's another student who's been working with us and with my research professor, Kristina Lilova, has a project really on sulfides, which fits into this, and we could then essentially have him work with us in the summer. So work for these students this summer is distanced, if you will. I meet with them, each student, about an hour a week. We have an almost Oxford-Cambridge style tutorial. A good conversation, I think one of the things we've proven is that you can have very good person-to-person contact without actually being face-to-face other than on the computer, and that's taught us all a lot of things. So right now then, the students that we have are these 2 young gentlemen, and Casey has finished her master's thesis. What follows is just a picture from the last in-person PIRE meeting, and smiling face then of our student Sally Burke from 2 years ago, and she's gone on to graduate school at, I believe it's University of California, San Diego, where she's in an environmental chemistry program of some sort. She was a chemistry major at Davis. So we were hoping to get pictures like this from this year's meeting, but I guess we won't quite. So let's talk about polymer-derived ceramics. From 100 years ago to the present, it was desirable to try to put carbon in one form or another into silica glass or glasses in general, with the thought of making materials that had some of the good properties of carbon, of graphite, in particular, and some of the good properties of silicate glass. The notion perhaps that you could make something that was electrically conducting and at the same time ionically conducting and at the same time had a glass transition was very exciting. But you could not do it directly. You could not do it directly by simply trying to melt together silica and graphite, because essentially there are high temperature parasitic reactions that make that impossible, plus the materials are very unreactive. So long ago, maybe 50, 60 years ago, chemists started experimenting with silica backbone organosilicon polymers with the idea that if you could make a polymer where the backbone was silicon, and the groups, the pending groups, if you will, were various organic groups, and then you would very carefully heat that polymer under anoxic conditions, that is, you would char the polymer, you would get something that perhaps would incorporate the carbon into the silica phase, since the carbon was already distributed on a fine scale, on an atomic scale in the polymer. And that indeed has worked and has indeed gotten the whole field of polymer-derived or polymer precursors for all sorts of interesting inorganic materials, for organic, inorganic, composite materials, and so forth. And the polymer-derived ceramics, classically in the silicon-carbon-oxygen system, or in the silicon-carbon-nitrogen system, or the silicon-carbon-nitrogen-oxygen system, have been studied extensively, and one has also been able to put other metals into them. And these materials have very interesting properties. What one knows about them is that they are amorphous to X-ray diffraction. So one says, oh yeah, this is some sort of black, tarry, uninteresting material. Well, it isn't. It's a very interesting material, and it's actually complex in its structure. The triangle diagram just shows in the black ellipsoidal region the compositions in the system that have easily been made into these polymer-derived ceramics. And the main notion then is that you take organic groups, you tailor them for the amount of silicon-carbon bonds they have, silicon-oxygen bonds, amount of carbon, amount of nitrogen, and then you carefully pyrolyze them, and the pyrolysis goes through a number of stages, and the final product is then your so-called polymer-derived ceramic that contains carbon that is part of the ceramic structure, and that's what we've been working on. And again, the tie-in with fibers and so on is that you can, of course, make fibers of these materials, and they have certain advantages and disadvantages compared to, say, silicon carbide fibers. So if we look at the pre-ceramic polymers, and this is something then that Gabriela Mera is an absolute expert at, one can design them, molecular structure, the structure of the, get the structure of the ceramic, and to get essentially the number of phases in the ceramic and the general properties. And the polymers can then direct the chemistry and physics of the polymer-derived ceramics. There are now a number of starting polymers that are commercially available. People use them, but another great art form is making one's own organic precursor to aim at a specific composition or a specific type of bonding. And that is something then that Gabriela is marvelous at, and that is something that our students who have spent time in her lab have learned how to do, and it's nothing that we really do, so this has always been a collaboration. If we take a look at some of the polymer precursor choices, one can of course choose different polymers to get the desired materials, to get the desired elements in them, and to get the desired structural elements. And all this diagram tries to do is show you that there's a wealth of things that one can do. And obviously, the better an organic chemist one is, the more one understands these initial synthesis steps. And we're fortunate, again, that we have had students that have a good background in both solid state chemistry and organic chemistry. So when they come to deal with these things, they're reasonably at home with it. So again, for example, we can use these two molecules as starting materials. So if we make polymer-derived ceramics out of them, they contain, and I thank Peter Kroll Casey thanks Peter Crow for some of these diagrams, one soon realizes that they're much more complicated in structure than something that is amorphous, random, and uninteresting. In fact, to a first approximation, they contain two hopelessly intertwined, what one sometimes calls Plummer's nightmare, fractal networks with a low fractal dimension. One network is carbon-rich and one network is silica-rich. The silica-rich network contains some carbon, and I'll come back to that. The carbon-rich network probably contains mostly carbon, and the carbon-rich network one can think of as distorted graphene-like sheets of a few, a few layers in thickness. They are not planar, they're distorted, they interact with the silica-rich part at their edges, but still they are primarily carbon-based materials. The silica-rich regions are essentially silica, but there's actual carbon dissolved in it, and the carbon substitutes not for the silicon, because although you can say both carbon and silicon like tetrahedral coordination, the bond lengths are just too different. Carbon is just too small to substitute for silicon, except under some very special ultra high pressure conditions that are not what we're interested in. No, the carbon doesn't do that. The carbon substitutes for oxygen. One doesn't have silicon nitride, silicon carbide in the material. One essentially has silicon that is bonded to 4 oxygens. That's the usual tetrahedral network silicon, or silicon that's bonded to 3 oxygens and a carbon, 2 oxygens and 2 carbons, etc. And one can tell the difference and actually count up the number of species, especially by nuclear magnetic resonance spectroscopy. Some of the more sophisticated forms of NMR also give you some spatial resolution that tells you that the number of these mixed bonds, the number of these silicon carbon bonds, is greater near the edges of a fragment of this silica framework. So the carbon content is near. The nearer you are to the carbon phase, the more carbon you have in the silica phase. Are these materials equilibrium? Not exactly. Are they steady state? Yes, they definitely seem to be. Are they a complex structure? Yes, they obviously are. And one still argues a bit about the size of these various domains, but there probably is a distribution of sizes. The end result as a material is these are interesting in terms of being hard materials, but hard materials with considerable elasticity. They are unreactive materials. They can be heated up to 1500 degrees centigrade and oxidize only slowly until you get some secondary reactions. They're lightweight materials. Some uses for them might be golf clubs, medical implants, catalysts, some ideas of using them instead of the carbon phase in batteries. I think this one makes these things better and cheaper. They will show up with all sorts of applications. But what we've really focused on then is the synthesis, structure, and thermodynamics of the polymer-derived ceramics. Here we show that indeed one can quantitatively count up the number of these different bonding groups, SiO4 groups, SiO3C, SiO2C2, so on and so forth. And the silicon magic angle spinning NMR gives a tremendous amount of useful information. This is just a spectrum of one of the polymers that was pyrolyzed to 1100 degrees C, which made the essential high temperature ceramic material. The biggest surprise early on in our first set of projects was that we found that if one looked at the energetic stability of the polymer-derived ceramic relative to its components, which would be SiO2, and it doesn't much matter whether you take quartz, cristobalite, or silica glass, plus silicon carbide plus carbon. If you take those as starting materials and you ask what is the energetics of formation of the polymer-derived ceramics from these, our early calorimetric studies showed that these reactions were actually exothermic. The formation of the polymer-derived ceramic from these end members was stabilizing. Furthermore, because the polymer-derived ceramic contains significant amount of disorder, it's almost certainly of higher entropy than the starting materials, so that makes it even more stable. So what we realized is that these materials are not just a, what should I say, accident of synthesizing metastable materials. They probably, in fact, have a thermodynamic region of stability, and that is something that we've been working on. So in the complex synthesis may just be a convenient way to get at these materials. Perhaps there are other ways of getting at them. And indeed, one of the things that we found in getting at them was to synthesize similar materials at much lower temperature and with higher hydrogen content. One can make low dielectric constant silicon, oxygen, carbon, silicon, oxygen, nitrogen materials with a lot of hydrogen in them. And these are of interest, for example, to Intel, and we've had projects looking at them. Laser ablation of a silica target. Take some silica glass, make a flat target out of it, put it in a vacuum chamber or a chamber that has some sort of gas, have a collection plate on the other side of the chamber, and then ablate the sample with a laser while it's in in contact with an atmosphere that contains carbon. Our initial experiments used acetylene gas. Collect the stuff you get on the other side, and lo and behold, it's nanoparticles of something like a ceramic material, like a polymer-derived ceramic, except the particles are smaller and it probably contains a bit more hydrogen. Well, if one thinks of hitting something with something high energy, making it vaporize, or at least making the particles, small particles, fly off, it begins to make one think, if one is geochemically inclined, of processes like volcanism and meteor impact. And if in fact one can make these silicon oxycarbide materials by this sort of ablation and impact mechanism, perhaps nature has been making them. So this has led us to think that some of these materials might in fact exist under various geologic and planetary conditions, and that is the, if you will, that is the connection in a way with materials of the universe. So the hypothesis, as we wrote it 6 months ago, and it keeps evolving, is that basically this sort of process, which occurs when there's some sort of highly energetic process in a planet, such as a meteor impact, such as deep-seated volcanism, such as perhaps even some initial processes in the solar nebula, that one gets a number of these materials initially, and that they gradually transform so that what is left after millions of years, billions of years, is not the original material, but it's some telltale traces. For example, some very refractory inclusions that have been in the original material. And the more you look for this, the more you think about it in a planetary context, the more it is plausible that something analogous to polymer-derived ceramics, something analogous to amorphous silicate phases containing various ions and carbon may be more common than we think. And this is something that we're still working on quite a bit. So getting back to the PIRE project, though, and getting back then to Casey's master's thesis, the goal of her master's thesis was to compare the energetics of polymer-derived ceramics, ideally at close to the same composition, made from precursors, one set of which would maximize the amount of mixed bonding, that is the carbon included in the silicate network, that is the SiO3C, SiO2C2, SiO3, etc. species, and then using different precursors where the carbon is not next to the silicon, making similar materials but that minimize the number of these mixed bonds. So she spent a lot of time in Darmstadt, good part of the summer of 2 years ago, and made a variety of materials. For various reasons, we were successful in making and characterizing the materials, but after we characterized the materials, we realized we were not successful in keeping their compositions the same. So some of what we're going to say has that caveat that we're not we're comparing systems with and without a lot of mixed bonding, but not at constant composition. And one would have to come back and do some more synthesis, and perhaps sometime we will. So here then basically is one material that we've made here, and this is, showing its spectrum. This is the pre-ceramic polymer synthesis route for those of you who like drawing organic molecules. And this is the NMR spectra of two of these samples, so one with and one without a bunch of mixed bonds, and one sees the difference very clearly. We've analyzed them then by NMR, we analyzed them by infrared, we've analyzed them by Raman spectroscopy. The Darmstadt group is finishing up or doing some electron microscopy that we would like to understand some of the microstructures, and Casey did the calorimetry at Davis before we shut down the calorimeters. So here is some example of some, again, some NMR, CP mass NMR of the groups to show again that one has the complex polymer-derived ceramic structure, and one has a gradient within the particles from the silica-rich interior to the carbon-rich boundary with the carbon phases. And where we are now, basically, we're just about finished with this project. So I could, gladly update this slide from what I presented in the Washington, D.C. meeting in March, because basically at this point the only thing that remains to be done is to finish the electron microscopy, and then take what is a fairly long master's thesis with a lot of introductory material and pare it down in the form of a paper that we will submit, and Casey is working on that. So let me talk a little bit more then about what we hope to do in the future. And this is probably something that I say is going to be involved in next year. Hopefully we'll be able to go to Germany and so forth. Whether Alex will be involved in that or something else, I'm not sure. We have a new PhD student, Michael Bustamante, from University of Houston, who has a good organic chemistry background. And since he's already in the States, he doesn't have a problem getting here, so he will be here for the beginning of our fall semester, and we will work him into the project. We hope to resume travel, of course, to Germany next year at some point, and we hope to continue working then with a German Deutsche Forschungsgemeinschaft research training group rather, that the Darmstadt group is part of. And some of our new directions, and I believe Isaiah will be talking or has talked about some of them, is to think about nanodiamond and carbon nanotubes within polymer-derived ceramics, and indeed using some of these silica-based materials as sort of porous, what one might almost call nanoreactors, for carrying out various synthesis reactions, transformation reactions. And we are meeting virtually with Gabi every month or so to keep this project going. So one of the most interesting things then is to synthesize these nanoreactor materials, and hopefully we will be generating them and generating products in them and doing calorimetry on the products to look at both the products themselves and their interactions with the walls of these so-called silicon oxycarbide nanoreactors. And we are interested just in nanodiamond, and indeed this brings us back again to a what should I say, planetary or exoplanetary or cosmic question, and that is that there's some evidence in interstellar dust, if you will, in interstellar space, that there are carbon nanoparticles, and that a number of these particles may in fact be nanodiamond, that is, tiny fragments of the diamond structure, probably with various other surface-absorbed molecules, because these nanocarbon materials have a great affinity for being slightly oxidized. And the question then is, can we mimic some of these things And indeed, can we say that perhaps some of these materials, when they came from space, they brought carbon, they brought water, perhaps more importantly, they brought chiral molecules, molecules that are left-handed and right-handed, so maybe those did not have to be synthesized entirely from scratch in the prebiotic earth. So all the way from materials that at one point one of the German auto companies thought of using for spark plugs to things that may exist in interstellar space, polymer-derived ceramics, nanodiamond, carbon materials of all sorts, silicon materials of all sorts. So I thank you for listening. I hope the thermodynamics did not put you to sleep. Thank you.